Well, welcome, folks. This is John Bergman.
Hey, hi. It's Mr. Sams.
Hey, you know, Mr. Sams, I was thinking.
Hmm.
You know, I was thinking of going on vacation.
Oh, yeah?
Yeah.
Where are you headed?
I was going to go to Milwaukee.
Milwaukee?
Yeah, Milwaukee, like chemistry moles. My favorite place, Milwaukee.
Yeah, it's a good place.
Yeah. I hear you've been thinking about getting a new haircut.
I have, you know. I'm thinking about going back, bringing the mullet back.
The mullet back. You know, I've been thinking about getting a mohawk.
A mohawk? Oh, yeah. We could pull the 80s haircut.
Yeah, it'd be pretty cool.
Nice.
Yeah, how would that look? I don't know. That's a... Right? Like that?
Oh, yeah.
That looks wrong.
Yeah, I don't know what that is.
Yeah, I agree. Hey, what's your favorite movie?
I kind of like The Incredible Mole.
Oh, I like that. You know, my favorite is The Last of the Mohicans.
Oh, that's a good one, too.
Yeah. I've always wondered, you know, I like to golf sometimes.
Oh, yeah?
Yeah.
You ever gotten a mole in one?
You know, I've been working on that.
Oh, yeah?
So, yeah.
Good.
Okay, yeah. Okay, all right. Hey, folks, podcast 15.1. Were those the worst jokes you've ever heard in your life? Hey, in chapter 15, this is what we're going to talk about. Common ion effect. What are buffers? Buffer capacity, titrations and pH curves, acid-base indicators, and the bells ringing, solubility, equilibrium, KSP, and then the KSP qualitative analysis.
KSP. It's grand.
KSP is very grand. So, hey, if you would just take your notes and we can follow along. Hey,
this one should be short.
This is a pretty easy podcast.
Yep.
Hey, common ion. What do you think common means?
Common means it's the same. Something's
the same. All right, so sometimes in an equilibrium solutions, they have more than one ion, and that ion is called the common ion. So, for example, when you take sodium fluoride and you dissociate it, it dissociates into...
Na+.
Now, you must have a plus. Why do you need a positive?
It's a dissociated ion, so it has to have a charge to be an ion.
You must have that charge. Now, Lee, I know you're listening. Lee, you must have the charge! Dun, dun, dun. Right, have the charge.
Yep.
Lee never leaves his charges, so I have to pick on it. Okay, so sodium fluoride. So here's the kind of the deal here. So if you have this reaction, this is HF is a weak acid. So notice I have the double arrow right here. And the H positive, it breaks apart in H's and F's. But if you were to add sodium fluoride, what does it actually do?
Well, you're adding sodium ions and fluoride ions. So what you're doing by spiking those fluoride ions, you're shifting the equilibrium.
You see, what I often see students do is that if they say they have a mixture of HF and NaF. The common mistake I see is they write HF plus NaF. Wrong! That's very wrong. Don't do that, please. Okay, it's very bad. Because you see, HF has a partner. His partner is F negative. And we've always said partners must always appear on opposite sides.
Yes.
So notice that in this reaction, the HF is on the opposite side as the fluoride.
Right.
And so when you add sodium fluoride, you are essentially, as Mr. Sam said a minute ago, spiking the fluoride. It's like an equilibrium thing. It's actually going to drive your equilibrium back to the left.
Yep.
Because you're adding a fluoride. You are not adding fluorides to the reactant side over here. You're adding it to the product side. That's very, very critical. Very critical. You screw that up, your host. Okay. Yeah. Hey, so let's do a little problem here. Actually, this is one we've done before, but you'll see how it applies in a moment.
Yes. All
right. So we have a solution of acetic acid. Acetic acid. Okay. CH3COOH. By the way, that also could be written how else, Mr. Sam?
HC2H3O2. Same thing.
By the way, just for fun facts to know and tell, the reason they write it as CH3COOH is an organic thing.
It's a structural thing. It tells you about where the atoms end up on the molecule.
So this right here is the CH3. CH3 is this piece right here. And then the COOH. It actually looks like this when we drew a Lewis structure. Yep. We'll learn how to do this when we do Lewis structures a little bit later. But this actually tells you the structure. This one doesn't tell you the structure.
Nope.
So this problem is just like an old chapter 14 problem. So if I have acetic acid, CH3, I'll write it this way, COOH. And that dissociates into CH3COO. It's actually this hydrogen here that breaks apart ours, and that needs a
minus charge. I was just about ready to say something.
Plus H positive.
I thought I'd give you a chance there.
I was doing a Lee thing on you just to see if Lee caught it.
Yep.
Did you catch it, Lee? Good. I'm glad you did that time. All right. So this was a
0.1 molar.
1 molar. Of course, there's none of this and none of this. Play the minus X game. So this is just like we've done for a long time. time. Long time. I've had a long time doing this. Okay. All right.
We need one more bit of information that's not given in the problem. That would be the Ka value.
And that happens to be
1.8 times 10 to the negative 5.
How do you know that, Mr. Sims?
I've done acetic acid a million times over in these
memorized
problems.
it. Now, you guys don't need to memorize that.
No.
That would be on the test.
Eventually, it just kind of gets stuck in your brain and rattles around there.
Over 0.10 minus x. So now first we get our solver out. And we take the solver. The solver x, if you recall, is equal to the concentration of the hydrogen. Are we looking for pH or what are we looking for?
We are looking for the percent dissociation.
So x is the concentration of the hydrogen, which is, by the way, also the concentration of the CH3COO negative. Gotta have the charge. And x is equal to, Mr. Sams is solving it on the solver.
Putting it in the solver.
So we're waiting for his fast calculator skills.
Here we are. Alpha solved, we have 0.00133.
So 0.00133 molar. So, of course, percent dissociation, you take x and you divide by the initial concentration times 100. So 0.00133 divided by 0.10 times 100 gives you
1.33%.
No, it's not. Yeah, it is. Sure. That's 1.33%. Now, that's just a problem we've done before. Chapter 14 took a test on it, so this is easy.
Why are you wasting our time?
Because guess what we just did?
Yeah, we led into this one.
We are leading into this particular problem, and it teaches something conceptual. A mixture that contains 0.1 molar acetic acid, like we did, and 0.1 molar sodium acetate. Now, what would be the common mistake that you would see?
The common mistake would be to put those added together on the same side of the equation, but we don't want to do that.
Like this?
Yeah, like that. That is wrong.
Because you see, what is the sodium acetate? The sodium is irrelevant ultimately.
Right, sodium doesn't do anything.
This is giving us a concentration of the acetate in the equilibrium expression.
Yes.
So we'll rewrite our equilibrium expression, C2H3O2. Now I'll switch back to the other one just because, I don't know, because I did. Makes H positive plus C2H3O2. Now this is a nice problem, ICE.
And we have 0.1 molar
0.10, and we've done this, but guess what we've done?
We also have 0.1 molar.
What did I forget, Lee? That's right, the charge.
I didn't even notice that.
I didn't either. 0.10. You see, what I've got here is now we have an initial amount of acetate.
Right.
The 0.10. There's still 0 hydrogen.
Right, because this is the starting. Then the equilibrium happens.
Now we just do the same thing we've done before. The only thing that's different is we now have something, we have an initial quantity over here. So plus x, so this is x, but this of course will be plus x. It'll be 0.10 plus x. So now we'll use our Ka, and it will be equal to x times the quantity 0.10 plus x over 0.10 minus x. That's I'm going to say 0.1, I think it's easier. And then the Ka, of course, is still 1.8 times 10 to the minus 5. Now, of course, you have to plug this in your solver. Now, by the way, when you plug this in your solver, I would do it this way. I would say 1.8 e negative 5 times 0.10 minus x, parentheses, minus x times 0.10 plus x. I think I got my pluses and minuses right, didn't I? I did. And that was set equal to 0. That's how I would type it into my calculator, and then I would ask what x is, and I think it's going to be awfully close to 1.8 times 10 to the minus 5.
Should be pretty close. And just checking my work here.
Mr. Sams is furiously typing on the calculator. He's been in the calculator. My kids used to call it the calculator. He's got the calculator working.
Up solve. 1.8 times 10 to the negative 5. It's actually 1.799999999.
The sig figs, it's 1.8. Now, why is that? Now, if you want to think about this for just a moment, since 1.8 times 10 to the minus 5 is a small number, and x is a very small number, when you add x and subtract x from 0.1, it is very close to 0.1. So these terms cancel. 1.8 times 10 to the 5 equals x. And it's not exactly like what Mr. Sam said, 1.79, but 9999 type deal. So this is close enough.
Pretty darn close. Now, we still want to do percent dissociation.
Now, the question wasn't what is x.
Right.
This is, by the way, the concentration of the hydrogen. But what is the percentage of dissociation? So the percent would be 1.8 times 10 to the minus 5 divided by the initial amount, 0.10, times 100. And the percentage is now much lower.
0.018%.
Now, let's kind of talk about what this means. Okay, what this means, when I had just the acetic acid, It was what percentage, Sam? Like 1.3 or something?
It was, yes, 1.33%.
And now we had
0.018.
0.018% with
Much
the
less.
mixture, right?
Yeah.
Why?
Well, we had extra acetate in there to begin with, so what that did is it's not going to let the reaction go as far right, or another way of looking at it is it kind of shifts the equilibrium to the left.
Yeah, that's exactly the point here. So we essentially added the 0.10 acetate, and that shifts this reaction back to the left.
Yep.
By shifting the reaction to the left, there's more acetic acid and less H's. And
Yep.
since X percentage is the X divided by the 0.1, since the X went down, the percentage goes down. So the more you add a common ion, the less, what would you say?
Less dissociation.
The less dissociation
Yeah.
is going to occur. So that is critical to understand that concept. Okay, we want to cover another section. By the way, when I say 15.2, we're actually now in section 15.2 in your textbook. So
Right.
if you're trying to follow along, we are using the Zumdahl 6th edition textbook for those of you out there in internet land. But this is commonly taught of all over the country. Okay, a buffer. Buffer?
Buffer.
Should I buff my car?
Yeah.
I like to buff.
I got one of those electric ones. You can
Oh
like
yeah,
a random orbit sander.
yeah, that's cool. I like
If
buffing.
I actually washed my car more often, I can actually use it.
You know, some people have said that I am buff.
Oh yeah?
Yeah, yeah.
Who are those people?
Lots of people.
Oh, okay.
Athletically, I'm buff. I got
Oh.
muscles
You got a lot more
coming
than
out
I
of my
do.
muscles. Not really.
I work on my...
You laugh too much.
Tummy
Okay,
muscle.
you shouldn't laugh so much. Your tummy muscle.
Yeah.
That's with cookies, I think.
I
isn't it?
know.
Yeah. All right. What? But that's not what we're really talking about
Nope.
today, are we? We're not talking about how buff Mr.
No.
Bugman is or how good you can buff your car.
Nope.
We are talking about buffers.
Acid-base solutions
Okay.
that are buffers, and what buffers do is they resist a change in pH. You guys have buffer systems in your body.
Yeah.
Keeps your blood at a particular pH, keeps your cells at a particular pH.
That is
Without them, if you drank a Coke, you would go into acidosis and you would die.
So this is very good that we actually have buffered, our blood is buffered. And so, but there are two components to a buffer. I say a buffer must have a weak acid, and number two, a significant quantity. Is the word quantity?
Mm-hmm.
Of the partner.
Could it also be a weak base in its partner?
Yes, hold on. So let's finish this
Okay.
idea. So the partner, and who is the partner? The partner will be the conjugate base of the weak acid.
Right.
So basically, I like to think they have to have partners in significant quantities. In significant quantities, I'm defining as by a factor of 10 of each other.
Mm-hmm.
So if I have a weak base, or a weak acid, so if I have acetic acid, the one we've been kind of playing around with here just today, the partner is acetate. So if this concentration is 1 molar, this concentration could be, say, 0.1 molar. Tenth of that, right? So
Yep.
they're within a factor of 10. Or,
Could be
conversely, it could also
10
be
molar.
10 molar. So it has a range of molarities. And if you have a significant quantity of both partners, then it is a buffer. Now, I just did an acid partner, acid-base partner. Mr. Sams, you were just alluding to that other one. What would you want to say there?
Like ammonia.
So you could have ammonia, which is a weak
base.
base, and his partner, which is...
Ammonium.
And ammonium is an H4.
Plus charge.
Oh, gotta have that
There's
charge!
the
I did that on purpose, actually.
Mm.
And that is a weak acid, or technically he is his conjugate
Yeah.
acid. But it has to be his partner. Now, you can't just
Yes.
have another conjugate acid.
No.
You have to actually have the partners. And, of course, what's the difference between partners always?
Hydrogen.
One hydrogen ion. You gotta have
Yes,
that
hydrogen
charge.
ion.
So to go from ammonia to ammonium, you add a hydrogen.
Yep.
If we go back to our previous example, to go from acetate to acetic acid, you add a hydrogen ion. So that's the difference.
Yep.
That's, frankly, what a buffer is. And I don't know if you realize this, but this example with the common ion we did just a bit ago,
We made a buffer solution.
we made a buffer solution right here. Yeah. See, because we had 0.1 of each. This is actually called sort of an ideal buffer because
Yeah.
you have exactly the same molarities of both. And so you have made an ideal buffer where they have, and you have both the acetic acid and his partner, or the weak base, conjugate base, acetate, and they are the same quantity. It just has to be within the factor of 10.
Has anyone
actually.
ever told you you're ideally buff?
I am ideally buff. My wife has said I'm the
well,
ideal
That
husband.
doesn't count.
She's amazing. She knows everything.
Well, yeah.
Yeah, well, that's true. Okay, all right. So now let's do an example here. Again, this is an acetic acid sodium acetate solution. Now here we've got some volumes going on here. So let's see if we can figure out what is the pH of a solution where 50 milliliters of 0.5 molar acetic acid, sodium acetate, is mixed with 25 milliliters of 0.25 molar acetic acid. All right, this is a little confusing. So what we need to do is actually, let me say one more thing about buffers. What units can you work with? Typically, you need to work with molarity units. And later on, we'll learn that you can actually, if it's buffered, only if buffered, you can actually also work with moles or even millimoles. And we'll do that as the unit progresses. All right, let's go back to this problem. Now, first of all, we've got sodium acetate and acetic acid.
Do not add them together.
I don't do this?
No.
Why not?
Because you don't put them on the same side. They're partners. Partners go on opposite
This
sides.
is wrong. You must not do the wrong thing. Okay, so you actually break it down. HC2H3O. You just write the regular equation, the dissociation of the weak acid or the weak base. So this makes hydrogens and acetates. Now, we do have an issue is that we want to work with molarity units. Okay, so let's think this through.
Yeah.
Okay, I have 50 milliliters of 0.5 molar sodium acetate. So I have 50 milliliters of 0.5 molar. So 50 times 0.5 is 25 millimoles. Now the way we got that, that's MV equals moles. And I'm leaving it in millimoles, so I do not convert this to liters. So I have 25 millimoles, and that's of the acetate. Now the other question, that's not brackets. And what was the other chemical I had?
Acetic acid, and you have 25 milliliters.
25 of
0.25
0.25. So I have 25 milliliters of 0.25 molar, and this is the acetic acid. And is that 12?
That's 6.25.
6.25 millimoles of the acetic acid. Now, since we want to work in molarities, I have a total volume when I pour these together of 50 plus 25, or 75 milliliters. So the molarity of this would be 0.33 molar for the acetate, and this would be 6 1/4 divided by 75.
0.0833333333.
And that's, yeah, molar. I didn't do that right. I didn't show that right, but you get the idea. So now I can go back to my equilibrium problem. And then the initial concentration of the acetate, did I do this right, Mr. James? 0.33. And this was 0.083.
Yep.
And this is my ice table. Minus X, 0.083 minus X. Now, I know this is buffered, by the way. How do I know it's buffered?
Because we have the acid and its partner.
So if you look here, highlighted in green, I have the partner and I have the acid, and they are within a factor of 10 of each other, aren't they? So now I simply just plug it into my cool Ka equation. We're working with acetic acid, so our Ka is still 1.8.
Mr. Bergman, your E for acetate is incorrect.
Oh, it's, yes, X, so 0.33 plus X.
There you go.
I was testing it.
I knew, I figured.
So X times 0.33 plus X. Now this one, those terms won't cancel, of course, because they are not the same number, are they?
Nope.
So now we plug it into our solver. So Mr. Sams is being the solver king right now, and he's going to solve for X. So make sure you know how to do that. That's important. We're not going to go for that right now, though. So X, and X is the concentration of the hydrogen. If you look at the equation, right? I'll go back here. X right here. I want to change that to pink. X in the hydrogen, right? And so X, when you do the solver thing, is equal to
4.5 times 10 to the negative 6.
So to find the pH, which the question asks for, the pH is the negative log of the hydrogen concentration, or this number right here, 4.5, and that comes out
5.34.
5.34. So the answer is 5.34.
Now, does that make sense?
Well, let's ask that
Let's
question.
think.
Okay,
We've got some acetic acid, and we have some acetate.
Okay.
So it's going to be an acidic buffer solution because we're dealing with a weak acid, and that's an acidic pH, so that makes sense.
Yeah. Now, one thing to note here, yeah, that's fine. I would say because the Ka of this is 1.8 times 10 to the minus 5, so it's a stronger acid than this is a base.
Right.
This would be about 10 to the minus 9. 9 and 5 is 14.
Yep.
And so this is a weaker base than this is an acid. Because if it was the reverse the case, it would actually be the other way around.
Right.
All right. And I think we have one more thing to do here, the Henderson-Hasselbalch equation. Yeah, we're almost done. All right. Now, there's a cool equation. I love this equation.
As do I.
The Henderson-Hasselbalch equation.
I called it the David Hasselhoff equation.
David Hasselhoff?
Yeah.
Why is
David
that?
Hasselhoff. Just because Hasselhoff sounds like Hasselbalch and it's fun to say.
Oh.
So then we...
There's a famous football player whose name is Hasselbalch.
Oh, we always called it then the Baywatch equation when I was in college.
The Baywatch
Because David
equation?
Hasselhoff was in this horrible TV show called Baywatch.
Baywatch. Oh, that's with the bimbos on the beach.
Exactly.
Okay,
Yeah, so we
I
just,
never watched
we just,
that show.
Yeah, I don't blame you. It's pretty dumb.
Okay.
But anyhow, that's what we
So here it is, pH equals pKa. We'll have to talk about what that means in a minute. Plus the log of the base over the acid. What does a sheep say?
Bah.
Base over acid. So that's all easy to remember. Okay, now what's a pKa?
Well, if pH is the negative log of hydrogens, then pKa is probably going to be the negative log of our Ka.
That's correct. So now, the beauty of this particular situation is that we do not have to do all this equilibrium problem we just did.
This is called a shortcut, folks.
We like shortcuts. So what we had to do is this whole big equilibrium problem right here. And I think, did I then solve? No.
For pH?
Yeah, if I want to remember,
solved for pH.
but we did, but we solved it the long way,
Yes.
right? So, so what I want to do now is I'll actually, you know, this last problem we got 5.34 when we just solved this, and so guys, what I want to do is under this space under the Henderson-Hasselbalch, I'm going to resolve this equation, use the Henderson-Hasselbalch equation. Now the first thing I need to do is I need to find the pKa. So the pKa is going to be the negative log of the Ka. Now the Ka in this case, if you recall, is 1.8 times 10 to the minus 5. So I just take the negative log of that and I get what?
4.74.
4.74. So Mr. Sams on his calculator has just typed that in. So the equation is pH equals pKa plus the log of the base, the concentration of the base, over the concentration of the acid. You probably don't need to recopy this down because it's right there on your paper. So I would say 4.74 plus the log of the base. Now I'm going to kind of make a huge parenthesis here because I want to do something interesting here. Now I want to go back where we found our concentrations up here, I think. Yeah, and so we had right here, I'll highlight it in pink, 25 milliliters over, or 25 millimoles over 75 milliliters. So I'm going to say 25 millimoles. Wait a second, is that the acid or the base? Am I mixing them up?
That one is the base. Yeah, you're fine.
Yeah, you got to put the base on the top. Millimoles over 75 milliliters. And then this other number was
6.25 millimoles.
6.25 millimoles divided by 75 milliliters. Now, let's just be mathematical, Mr. Sams. What do you see? You could you simplify
Oh yeah,
this
let's
expression?
cancel 75.
You see the 75s, that color doesn't work, does it?
Yeah.
How about this color? The 75s cancel, don't they?
Yep.
So you do not have to actually calculate the molarity like we did
Nope.
just a bit ago.
If you have millimoles, it works in the buffers.
So all we need to do is take, on our calculator, 4.74 plus, so I would type it in, 4.74 plus log, parentheses, 25, divide, 6.25, parentheses, equals
5.34.
5.34. And that's, folks, the answer we got earlier. All you would have to do is use Mr. Henderson-Hasselbalch. Now, a caution. When does Mr. Henderson-Hasselbalch equation apply?
Only in buffers.
What's a buffer again?
You have to have a weak acid and its partner.
So,
or a weak base.
if you just had a weak base,
Mm-hmm.
could I use it?
Nope.
Just a weak acid?
Nope.
No. I have to have the partners.
The partner.
Must have the acid and his partner, or the base and his partner. Okay?
Yep.
Now, on the base problem, just as a quick note, if I were to use the Henderson-Hasselbalch problem and I had a base, I would have to, usually you have the Kb. the equation says Ka. So you'd have to find the Ka using the Ka times Kb equation.
Yep.
So that's something to keep in mind as you did. All right, let's do a couple more examples here. Okay, calculate the pH of the following solution. Now we're going to use the shortcut method because it's better. Okay, better is shorter and good. Now I think this is a buffer. We got to double check. What have we got? We've got hypochlorous acid. So we got HOCl. And what do we know about Hocl? All right, what do we know about the Hocl? We've got 25 milliliters, and it's 0.150 molar.
Yeah.
Now, if you use the MV mole things, how many millimoles is that, Mr. Sims?
3.75 millimoles.
Okay, and then we've got KOCl. Now, in the KOCl, who do I care about?
OCl.
Just Mr. Sims.
It has a minus charge on it.
OCl negative.
Yeah.
OCl negative. What do I know about OCl negative? I've got 0.45 molar, and I've got it at 32 milliliters. So if I take M times V,
14.4.
14.4 millimoles. Now, do we have a buffer?
We do. We have a weak acid and its conjugate partner.
And they're within a factor of 10.
Yes.
So now, to find the pH, we can use this cool Henderson-Hasselbalch equation. So we can say the pH is equal to the pKa plus the log of Ba. Right?
You have to look up Ka.
So you then have to look up the Ka of HOCl. So let's fix that out here. So the Ka, I'll come back to that screen. The Ka of HOCl is equal to, the value of the Ka is
3.5 times 10 to the negative 8.
10 to the negative 8. So Mr. Sams is going to take the negative log of that.
Negative log
of the Ka.
3.5 times 10 to the negative 8.
Be 7 point something, right?
7.46.
7.46. So now I'm going to go back to this screen here. So that's going to give 7.46 plus the log of the base. Now I got to go back. The base, let's think this through. The base, this is an acid, and his partner is a base. So the base is the 4.4 number. So that'll be 4.4 divided by, now I go back to the acid, I can't keep this in my long-term memory very well. Oh, it's 14.4 over 3.75. Most of you probably caught that because you had the papers in front of you. You simply just type that in and you get
8.04.
8.04. So this could be done the long way, okay guys, like we did up here. So you remember this problem right here. We could go back and do this problem and do the x, minus x, plus x, da-da-da, get the Ka, or we could just use Mr. Henderson-Hasselbalch equation and we become happy campers. We like happy campers. It's good.
Yep.
Okay? All right. Oh, actually, you know what we're going to do here? You know what I was going to do on this? We've already done this before. This is where we simplify. We're going to just skip this slide. It's unimportant. I've already shown this concept to you. And then we do want to do one more where we have a base and use the Henderson-Hasselbalch equation. All right, what have we got here? We have the pH when we have 25 milliliters of 0.5 molar methyl ammonium nitrate. Now, that sounds like a nasty chemical. Methyl ammonium nitrate. Now, guys, if you would take your book and open to the appendix, or those who don't have the books or whatever, you need to find a table of KBs.
Yep. And
you could, one of the common ones is this thing called
methylamine.
Methylamine. Let's do methylamine first because he's easier. You'll find him, and his formula is CH3NH2.
Yep.
And what we know about this character is that he is 75 milliliters, and it's 0.30 molar. So his millimoles are, Mr. Sams is going to take M
right, we got
times
22.5.
22.5 millimoles. And then the methyl ammonium, or ammonium, is just going to have one more H. That's CH3NH3 positive. And that's reacted with, technically it's CH3NH3NO3. But the nitrate breaks apart, or breaks off, and you're left with this guy right here.
Nitrate never affects pH.
Nitrate doesn't affect pH. So it's 0.50 molar, and it's 25 milliliters. So when you multiply those out, how many millimoles?
12.5.
We have 12.5 millimoles. Now, do we have a buffer?
We do.
So with a buffer, we can use the
Henderson-Hasselbalch.
So we now have our numbers, 12.5 and 22.5. Now, we do have a particular instance. So when you look in your table in the back of your book or in a table, we can look up the KB of a methylamine, CH3NH2. And that value, Mr. Sams, is what from your book?
It is 4.38 times 10 to the negative 4.
Now, in the Henderson-Hasselbalch equation, it says
right.
pH equals pKa.
Ka.
This is a Kb.
Yep.
So I need to find the Ka. And remember, the Kw divided by the Kb equals the Ka. Or that comes from the equation Ka times Kb equals Kw. So when you get the Ka, you get
2.28 times 10 to the negative 11.
And of course, we're going to find the pKa. So if you take the negative log of this value here, you'll get the pKa, and that'll be 10 and some change. Am I correct?
Yeah, it is. Sorry, hang on.
Mr. Sams is fiercely.
I was starting on something else. 10.6.
10.6. So you've got to find the pKa. So there's a little additional step here if you have a base problem. So now we can use our Henderson-Hasselbalch equation. pH equals 10.76.
10.6. 10.64 if you want another 60.
10.64 plus the log of the base over the acid. So let's go back and figure out who was the base and who was the acid. All right, the base is the methylamine, and his conjugate acid is the methylammonium. So it'll be 22.5 over 12.5. So I'll say 22.5 divided by 12.5. And that's it, folks. 10.64 plus this log, and you're done.
We get 10.90.
10.90. So that's the pH of this solution. The only trick on this particular problem is understand this Ka, Kb, Kw thing. And probably the other trick is this screen here, is that you have to understand who is who. Actually, I think this is the problem everybody has, is to understand which chemicals you're dealing with. Methylammonium, nitrate, that sounds like just this horrible thing to name, but if you find methylamine, then they're giving you his partner, and you ignore, cross them out, the nitrate. You have methylammonium. Okay? Folks, this will get you lots of things to get started on the whole concept of acids and bases, acid-base buffers, because you see, I am buff. You know, I've been thinking about taking a trip, Mr. Sams.
Oh yeah, where to?
I was thinking about buying a, well, it's actually where. Well, I was going to Milwaukee, but
yeah, that's right,
a new
you're going to
vehicle. I was thinking about getting a new vehicle to get me there.
What do you get?
I was going to get the Millennium Falcon.
Millennium Falcon?
Yeah.
Oh, you mean like things from Star Wars?
Yeah.
Oh, that'd be kind of
might
cool.
fly me there faster than
hyperspace.
hyperspace. Yeah. I've also been a little bit hungry lately.
Oh yeah, what are you
It's
going to
kind
have?
of around lunch. I was going to get some moldy bread.
Ugh.
Yeah, I know it.
Doesn't sound very good.
Well, it's a lot of protein.
Yeah. Well, we promised you a short podcast and we lied. We're sorry.
Have a great day.
Bye guys.